What's up, Mindsetters, grade 11s? It is your time for physical sciences on this beautiful Tuesday. I am Looney, and joining me in studio is one of my favorite teachers, Tracy. How are you?
Finally,
I'm good, thanks.
You can come back.
Yes, like all the time, Tuesday.
Absolutely, yes. There we go. Yes.
So what are we doing for the Mindsetters today?
Today we're going to carry on with acids and bases. Remember, guys, last week we did the basics. We started at the real beginning. What are bases? What are acids? Today we're going to look at strong and weak acids and bases. We're going to look at some common ones. We're going to do a attempt at a titration, not a complete one, and then we're going to look at some reactions. So you're going to be able to have to put, when I give you things, can you get me the products at the end, basically.
That stuff. So today it's not chilled, it's all full-on lesson.
Today's a little heavier than last week.
All right. Mindsetters, you heard it. We're going full on with acids and bases part 2. This section used to haunt me in my dreams back in the day. So I hope you guys do enjoy it. Thank you so much for tuning in. Remember to hit us up on Twitter @LearnExtra, on Facebook. Our page is facebook.com/LearnExtra. And remember to download all the notes, the schedules, the videos on LearnExtra.co.za, and anything else you'd like to know about Mindset Learn and Learn Extra Live. Just simply go onto our website, guys, and work your way onto our page and all of that stuff. So with all that said, I will tell you about the Stars in Education Awards throughout the whole show. But for now, let's take it back to Tracy with our awesome lesson.
Thank you. Anyway, so we're starting with acids and bases, guys, and what we're going to start off with is just to go through what we're going to do today. We're going to look at the difference between strong and weak bases. This is really important with weak and strong acids as well, and hopefully get the misconception of concentration out the way. We're going to discuss some acid reactions, so what happens when we put an acid with a base or an acid with a metal, which you did do in grade 9, hopefully. Discuss neutralization reactions, got a little bit of an experiment going for you, and Looney's upset with me because I don't know if I'm going to need your help today.
Why exclude me? But it's
I
fine.
know, I'm sorry.
It's fine.
And then we're going to discuss indicators, okay? So, starting with, what is a strong and a weak acid? Now, what's really important here is we define a strong acid, an acid which ionizes almost completely. Now, I've deliberately gone and bolded and underlined ionize, because you've got to remember that all your acids are covalently bonded molecules, grade 11s. So that means they're not naturally ionic. So they haven't given away electrons, they haven't taken electrons, they're sharing them. So what happens is when the acid dissolves in water, we have to force it to become ions, and that's really, really important. With a strong acid, it desperately wants to become ions. So when we look at a strong acid like hydrochloric acid, when it reacts with water, and what's very important here is that we say it is reacting with the water, it's part of the reaction, okay? We end up with H3O plus ions because what's happened is the chlorine, the hydrochloric acid, has given its hydrogen away. It's acted like an acid. Remember, acids are proton donors. We did that last week. The water acts like a base, takes the hydrogen, ends up with H2O plus and Cl minus. Now, this is a strong acid, so that means when I look at this, if I could look at this solution from in a microscope and I could actually see the little molecules everywhere, there would be lots of H2O plus and Cl minus. And remember, I said to you last week as well that it's this H3O plus that makes it so dangerous, okay? It's the H3O plus ion that corrodes, that eats away skin and metal and all those wonderful nasty things. Moving on. So, when we look at a weak acid, and it's hard to see it from the equation because of the way we write the equation at this level. When you get to grade 12, you're going to do a thing called chemical equilibrium, and you're going to do the whole thing with reversible reactions, which you've seen. And this is, we're going to rewrite these equations with the sign doing this. Little sign to the right, sorry, big sign to the right, little sign to the left. And that tells me that I have lots and lots of ions in there. With my weak acid, like acetic acid or ethanoic acid, vinegar, okay? Remember, it's only that little hydrogen at the end that's important. The one that's bonded to the carbon isn't important, okay? It doesn't make it acidic. That hydrogen comes along, donates itself to the water, okay? Off it goes. Once again, we get H3O plus ions, and now we get the CH3COOH minus, okay? This is a weak acid though, so what that means is that when this dissolves in the water, we get it to ionize, but we don't get a lot of product. There's very little of this. So because there's so little H3O plus, it's not very dangerous. Doesn't mean that it can't do damage, okay? So what I'm saying to you is don't go and drink a whole bottle of vinegar. You are going to feel fairly sick after that if you can actually get it done. Okay, so you've got to be careful because remember your stomach's got acid in it. You don't want to add to that, okay? But lucky for us, vinegar, if you spill it on your table at home, isn't going to eat through your table, okay? Which is a good thing. So acids, ionize, very, very important. A base, before we get there, now I've got a list here. And this course is in the notes you can download. Please, grade 11s, you have to just learn this. This isn't something where I can say to you, look at the structure, look at how many hydrogens there are, because it doesn't work like that, okay? And these are your common acids. So these are the acids you're most likely to find at school. These are the ones we're going to deal with calculations, with experiments, all of that sort of stuff. And they expect you to know whether they're strong or weak, particularly for next year, because next year we're going to look at titration in a lot more detail than we're doing this year. And in fact, you're going to have to calculate final pHs. It's going to get all nice and hairy for you guys. It's great fun. And from knowing whether you have a strong acid and a strong base, you have to choose what indicator you're going to use. So that's really, really important. And unfortunately, this is one of those things you just have to learn, okay? I know, I still get confused at times, but I know them because we use them all the time. First four, hydrochloric, nitric, sulfuric, phosphoric, these are all strong acids. Phosphoric isn't that strong, but it's still classified as a strong acid. Then we get carbonic, and remember I told you last time, carbonic acid is what you find in your fizzy cold drinks. In fact, you find a little bit of phosphoric acid too, okay? And carbonic acid's the one that they reckon will rot your teeth, and you can use to marinate meat, and all those fun things, okay? Ethanoic acid, which, is vinegar, and then oxalic acid. This one's quite an unusual one. Don't stress at this point about its structure and the fact that it's COOH in brackets. You're going to deal with it when you do organic, okay? The nice thing about these two is you're going to remember how to name them and draw them when you do organic chemistry next year, which is actually going to be a lot of fun. Okay, so that brings us to bases. Now, a base dissociates. There's only one exception to that, and I'll talk about that in a second. Bases dissociate because bases are ionic. Bases are made up of your negative ion, which is usually OH, but it doesn't have to be. It can be nitrogen, it can be carbonates, it can be oxygen. So it's a negative ion with a metal, generally speaking, except ammonia. Ammonia is your exception to this whole thing. So ammonia is the only base you have that's covalent. Most of your other bases are ionic. Now what that means is when they get added to water, they split apart. They dissociate from each other. Much like water's like that third wheel. You know what I mean? You have a friend and you're best friends, and then water happens. Generally it's a boy, okay, if it's two girls, and then you decide you don't want to have anything to do with each other anymore, okay, because, water got in the way. And if you don't, sometimes that dissociation is fairly permanent, and sometimes you actually manage to get over it and, kick the boy out and you become friends again. All right, but what does that mean? Water doesn't actually take part in the reaction. So look at the difference in the way we write this. Here I have sodium hydroxide. The water gets put on the top. It gets put in the arrow because it's not part of the products. And literally, I'm splitting the sodium hydroxide in half. So I'm breaking it up into its ions, Na plus, OH minus, okay? I could write it with the water in the middle, so then I'm going to get the fact that water's starting to act like a acid in this case, but that gets quite complicated with what we're trying to do, okay? But it's a strong base. NaOH is a very, very, very strong base. It's caustic soda. It is extremely dangerous, okay? It's not one of those things you should have in your home, and if you do, I'm a little worried. And it's one of those things that we use as industrial cleaners, very, very dangerous. Can burn you, and this is one of my pet peeves, it can burn you as badly as an acid can, okay? And in fact, when you mix sodium hydroxide into a solution, if you're not careful, it can bubble up so much that if it gets in your eye, it can blind you. It's very, very dangerous, okay? And Looney, remember last week we spoke about that episode of the program? It's actually CSI.
Yes, yes.
And the guy falls into the pool. And
yeah.
it's not pretty. And it's only with organic material. Sodium hydroxide loves organic material, okay? So I'd be fairly safe in my clothes because I think most of it's synthetic, so we'd be fine. Okay, your weak bases, something like your carbonates, generally carbonates are weak bases, also dissociate, breaks where the metal is, breaks up into two, okay? What's important here is you've got to remember what your polyatomic ions look like, what their charge is, and all of that sort of thing. Now, there's an exception, grade 11, so I want you to just pay attention to this, and that's ammonia. Ammonia is actually a weak base. We use it at home a lot. It's a very good cleaning agent. You smell it in Handy Andy and all of those sort of products, so they are moving away from it because it's toxic. Not because it's a base, but just because it is toxic, just in the format that it is. And ammonia has that very pungent, it feels like it's burning your nose and your eyes, and it's just not pretty. And in fact, you get fibs ammonia, which is only, I think, 33% dilution. But if you don't wear gloves when you use this, it actually burns the first layer of your skin, and your skin feels like leather and it peels. And yes, I'm talking from experience, but we'll move on. Okay, always read the instructions. I'm just saying. Yeah, I was young.
Okay, at least you weren't like now. I'd be surprised.
No, I learned my lesson the first time. Anyway, now, with ammonia is going to have to ionize, okay? Ammonia is not ionic. It's two nonmetals, which means the water is going to act like an acid, give its hydrogen to the ammonia, and it's going to give us the ammonium ion. So that should be plus, and that's minus. Now, you've seen this before, grade 11s. Beginning of the year, you did covalent bonding, and you did dative covalent bonding. This was one of the ones you had to learn to do. So there's lots of stuff involved in the ammonia, okay? And remember, this is my base, this is its conjugate acid. Ammonia is your exception to dissociation. It ionizes. Now, just like with your acids, you have to learn your list of strong acids and bases. See, Looney, the board doesn't like me again. I'm telling you. Okay. Generally, now this one, it's a little bit easier to find a trend, because if you look at all my strong bases, ammonium hydroxide, potassium hydroxide, calcium hydroxide, magnesium hydroxide, there are exceptions. These are the ones you need to know. The hydroxide makes it a strong base, okay? The rest, now we've got carbonates. Carbonates are actually very weak bases, which we're glad about, because remember, sodium bicarbonate, baking powder. You use it at home. You don't want to be using things like sodium hydroxide when you cook cakes, unless you're trying to kill someone, which we do not approve of. No. Okay, so your carbonates are weak bases. Very, very important. Your hydroxides are strong bases. Okay, so, you know what? I know we're a little early, Looney, but I don't want to get halfway through doing this section, so we'll take a break and then we'll come back.
All right, cool. Yeah. Just a quick shout out, special shout out to Lovejoy, who says Tracy makes physical sciences seem so easy. So that was a special shout out to you, Tracy. Mindset is we are going to take a very short break, so don't go anywhere. We will be back straight after this. Welcome back, Mindsetters, from that very short break. I hope you guys are ready to learn more and learn extra with Looney and Tracy. If you've just joined us, we are doing physical sciences, acids and bases part 2. So I hope you guys are ready to learn more with Tracy. Tracy.
Thank you, Looney. Okay, now we get to the fun part, okay? So we're going to do a little bit of experiment in a couple of minutes, but first we need to talk about our chemical reactions with acids. Guys, I promise you, you have done this before. The issue now is for you to remember them, all right? Learn. Please don't try and learn 4 million of these reactions, because you can't. The way your teacher knows what things are going to happen is they know the general, okay? So, for example, okay, we're going to start with the fact that an acid plus a metal gives us salt plus hydrogen. And I really am hoping you've seen all of these. Okay, unfortunately we don't have time to do them, but I really am hoping you have. But if we look at the first one, it's an acid plus a metal. So let's keep them nice and simple. So if we go hydrochloric acid plus, let's make it magnesium. Okay, it's going to give me a salt plus hydrogen. The hydrogen part's easy. Okay, now to work out the salt, what happens here is we go, well, the acid's going to split in half. I've already used the hydrogen, so I made the H2. So the chlorine's going to bond with the magnesium. Okay, chlorine's going to bond with magnesium, which means I'm going to make magnesium chloride. And here's where being able to write formulas is very important, because we recognize that it's MgCl2, and of course we can't leave it looking like that because your teachers will be very unimpressed with you. So let's write it properly. That would be HCl, and it would need to be a 2 in front of it. Grade 11s, as this must become second nature. So maybe when you write a test or exam, make a big note for yourself on the top of your paper and go balance chemical equations, okay? Make sure you always balance chemical equations. That's very, very, very important. So that one's not so bad. The next one, acid plus a metal oxide, okay? Let's take sulfuric acid. Let's take, be a little bit different, okay? And we need a metal oxide, so we've already used magnesium. Let's use sodium oxide, okay? It's a little more difficult, so sodium oxide would be Na2O. And now we go, okay, gives me a salt plus water, which means I know the N's going to be plus water. The salt comes from the fact that the hydrogen and the oxygen make the water. Makes sense, hopefully. And this is a swapping partner thing, okay? The plus hydrogen plus oxygen minus go together, which means the sulfate, which is minus, goes with a positive Na. Once again, make sure you can write formulae, but this becomes Na2SO4, and that's already balanced. So that one wasn't so bad. That's actually quite a nice one, okay? Then we have, and this is the one you're going to see often, acid plus a metal hydroxide. Okay, so let's take HCl again, and this is the one you're going to see most often. HCl and sodium hydroxide, NaOH. Hopefully you know this. The nice thing about this reaction is that it gives us a salt, otherwise known as table salt, NaCl, okay, plus water. Grade 11s. And I've had this discussion with my learners recently. You really struggle with the concept that we call some of these salts, okay? Simply because we're so used to, you know, you go out for dinner or you're at the dinner table and you say, pass the salt, okay? What do you mean by pass the salt? You mean pass the sodium chloride, okay? Sodium chloride's common name is table salt, actually, okay? But we just shorten it to salt. Could you imagine every time you went out for dinner and went, please pass me the table salt, or pass me the sodium chloride? I think people are going to start looking at you funny.
Yeah,
maybe I should start trying that. No.
Pass me the sodium chloride, please.
No. Yeah, I'm going to get some funny looks. All right. But what that means is in your head, and I can understand it, is you go, salt must be sodium chloride. No, 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 no. A salt is the name given to an ionic compound, okay, with a metal and a non-metal. They are salts, okay? When the ionic compound comes together, it is a salt, okay? So keep that in the back of your mind. Now the more difficult one. Acid plus a metal carbonate. Now, carbonates are your weak bases, okay? So let's take HCl, let's not make this too difficult, and add it to sodium carbonate. Na2CO3, okay? Now, the reaction says to me, I'm going to get salt, which hopefully you guys are screaming at the TV going, no, I know what it's going to be. Sodium chloride, absolutely, NaCl, plus water, H2O, plus carbon dioxide, CO2. And to balance it, I need a 2 in front of here. Where does the CO2 come from? It comes from the CO3, okay? The CO3 gives me the CO2. The one oxygen from here also ends up with the water, and so it splits up, okay? So if you ever a little confused as to whether I'm going to get carbon dioxide, you must have the carbonate in it, okay? We're going to do lots of these questions at the end, okay? Now, neutralization reaction. This reaction is sometimes a little bit more difficult to understand because you hear neutralization reaction and you go, okay, it must become neutral, so if I put an acid and base together, it becomes neutral, everyone's happy. No, okay, because a neutralization reaction is simply the reaction between an acid and a base, okay? It is simply the reaction between an acid and a base, and the reaction is called a titration, okay? It's the reaction between an acid and a base, and it's called a titration, okay? So the thing I need you to not be thinking about is that when I have a neutralization reaction, then I'm going to end up with 0, okay? I'm going to end up with a pH of 7, okay? So be careful with that. Now, in the notes, we said we're going to do an acid-base titration, and I'm going to show you something a little less as complicated as the acid-base titration, and we'll talk about this in a second. So what we're going to do is we're going to come over to my lovely spot to play, and I'm actually very excited. I got laughed at a little bit earlier because we have universal indicator paper, which is brilliant, and this is just a paper form of universal indicator liquid, and I have litmus. Hopefully this is the one you guys have all seen, okay? You've all seen, oops, I'm busy throwing it around. You've all seen blue litmus, okay? You've all seen, oh look, it matches my nails. That wasn't deliberate, okay? So you all see blue litmus paper. And this is the one indicator you guys all can tell me. So if I take some blue litmus and I'm going to put it into my first test tube, and we're going to see what happens. Okay, it's going to get it a bit wet. There we go. And I have my white paper, and we all see it went pink. Yay! And hopefully you guys are scaring the TV. Let's not scare the TV. Let's scream at the TV. That means this is an acid. Absolutely, okay? This is one of our indicators. Now, what I actually have in this test tube is a solution of acetic acid, otherwise known as vinegar. And I'm now going to add in some phenolphthalein, which is colorless, okay? If you look inside my pipette, you can see it's colorless at the moment, okay? Put a few drops into my acetic acid. Oh, look, that was exciting. Hey, Looney. Yes, nothing happened because phenolphthalein is colorless in an acid, okay? That's what makes it special. Now I'm going to do a neutralization reaction, okay? If we were doing this as a titration, and I'm going to show you that this is the acetic acid, that won't actually help us. I'm just going to make it more colorless, if that's at all possible. Okay, here we go. I'm going to put sodium hydroxide in. Now, what we're going to see is I'm going to put the sodium hydroxide in, and I'm going to put a little bit in. It's a fairly, okay, nothing happened. If I was doing this as a titration, I would do this step by step. Okay. Oh, look. And it doesn't want to change color. Okay, it was a fairly strong sodium hydroxide solution. So I'm going to add a little bit of water to it. See what happens with live TV. Oops. Okay, what we're really wanting to do is show you phenolphthaleine's beautiful pink color. Okay, I'm going to, what should happen, and I've run out of space in my test tube, okay, is it goes pink. So give me a second, we're going to come back to it, okay, I will show you the pink color. I'm now going to deal with my hydrochloric acid. Okay, I'm going to put some universal indicator. Now, universal indicator is a great indicator because it goes a whole bunch of colors. And there we go. Okay, oh, let me just show you quickly. If you look at it, I'll put it up on my... It's a bit hard to see, but it's a greeny blue color, and my hands are busy going all sorts of colors. It's great. Okay, universal indicator has this wonderful range of colors because it's actually a mixture of indicators. It's great. We love universal indicator. Anyway, so in my acid, this is hydrochloric acid. I'm not going to dip anything into there. Okay, I'm now going to add my sodium hydroxide, and I don't think my sodium hydroxide's working. Oh, no, wait. Can you see it's it's not as pink? Okay, it's not there yet. Let's do this again. Okay, I could be doing this till the cows come home. I do apologize, guys. We thought my sodium hydroxide solution is actually just not strong enough. But add a little bit of water. Hopefully that'll dilute my acid a bit more. And let's... No? Okay. It's actually quite difficult to see, but what we're going to do here. Okay. And just so you know, this happens in my classroom too. Universal indicator paper. I'm going to put it in there, and it's actually quite a nice, actually I don't need to do this, quite a nice red color. And if you look, I've got a chart. Every universal indicator pack or bottle of indicator has to come with a strip. And this actually probably looks like what you see in your pool tester kits, okay? Because it's essentially what it is. And then I can compare the color. Now this has gone far, it's not as red as it was, which means it has changed pH. It's going more orangey. It's more orangey now, so it's more 5. I think the honest truth is my sodium hydroxide is just not quite strong enough. What I'm going to do is I'm going to put my sodium hydroxide into my last test tube, okay? And I'm going to add some phenolphthalein to it, and we're going to see it turn pink, hopefully. That's what I wanted earlier. Okay. Isn't that a beautiful color? Hey, Looney?
Oh,
how pretty is that?
That's very
That's
nice.
what I wanted. Unfortunately, the issue isn't that the sodium hydroxide isn't strong enough. Okay? It's not that it's not strong enough. It is a strong base. It wasn't concentrated enough with the concentration of these. Okay? So that was part of the issue. But this is actually such a beautiful color. Now, what I'm going to do is I'm going to take my universal indicator paper, because to add universal indicator to this is a bit silly because it's already pink. I'm going to use the paper, and I want you to see this. You'll see this actually very nicely. There we go. Can you see? Look how purple it is. Okay, it's gone very purple. Doesn't match my nails anymore. And if I put my strip with it, okay, let me do this rather. Sorry, it's all about coord. Let's hold it. Okay, if you put it close to the strip, can you see that it's close to the 14? Okay, which is what we didn't have earlier. Okay, the point here is that unfortunately this wasn't concentrated enough, so I didn't have enough sodium hydroxide ions in here, molecules in here, to make these change color. I mean, I can add this to here, I think, until, like I said, till the cows come home, and I add a little bit more to this one. No, see, the color disappeared immediately. Did you see that? It's pink. Let me hold it a little bit further down. Color goes away completely, okay, because this is a very, very strong solution, okay? It's a very concentrated solution. If I take the litmus paper, if I take all of it, not just a piece, okay, and I put it in here, you saw it go red with the acid, stays blue, okay? This is very, very important. It stays blue. If I put this in here, it goes pink. Okay, pink or red in an acid, blue in a base. All right, now just before we go to the break, I'm just going to talk a little bit about what the setup would be if I was doing a proper acid-base titration. Is we would put our known solution, standard solution, in the conical flask. Usually, it's the base, okay? We put the acid into the burette. We don't like to put the base into the burette simply because the base might clog up the burette. We add a suitable indicator. Universal indicator is not great for titrations, okay? So we use phenolphthalein, bromothiamyl blue, methyl orange, methyl red. You'll need to know which of those next year, so don't stress too much about that. And then we add in the acid, and we add it in until a single drop changes color. We've then reached the neutral point. We've then done a successful titration. We weren't very successful today because you didn't see the color change as much as I would like, but that's simply because we were using the test tubes, okay, and my hydrochloric acid solution and my acetic acid solution were too concentrated for my sodium hydroxide. My sodium hydroxide should have been a little bit more concentrated, then I would have used a little bit less. Okay, so what we're going to do, Looney, is we're going to take a short break, I think, and then I'll come back and I've got a really cool animation to show them.
All right.
Yeah.
Mindset says, let's take a very short break. Shout out to Homo, who says, wow, Tracy, thank you. You rock my physics. I enjoy it. Thanks to you. Thank you so much, Homo, for tuning in. And Mindset says, we'll see you straight after this break. Enter your teachers. I will post all the information you need on our Facebook page. Basically what they're looking for is they want to recognize the teachers that play a role in shaping your futures, in building your characters, and not just only education but you as a whole. So they want to recognize and acknowledge and appreciate your teachers. So tell me who your favorite teacher is. Tell me why you want to enter your teacher, what's special about them, how they've impacted your life, and enter them into the Stars in Education Awards. If Tracy was my teacher, I'd nominate her. So guys, please make sure you check out our Facebook page for that. And with all that said, I'll hand it straight back to Tracy.
Can I record that and send it to my kids?
Of course you can.
I'm just checking. Guys, seriously, as a teacher, I have to be honest, it's not about the gifts, but when you say thank you to your teachers,
yes.
And you know, some of your teachers work very, very
yes.
hard. So think
yes.
about it. You know that there's that one special teacher who, you know, would do absolutely anything for you. And it's actually... it's a nice way to say thank you.
Thank you, yes.
You know, and I mean, as me as a teacher, I've been teaching for a long time, and I have every single note my kid has ever given me.
Oh, that is so cute.
Every single one. So, and then when I feel like, why am I teaching? I take out my little box and I read them, and then I cry, and then I get over myself. Anyway.
Before you start.
Oh, sorry. Yes.
Question from Elebocheng or Lebocheng Seribe. What are metal oxides?
Okay, sweetie, all a metal oxide is a metal bonded to an oxygen. So, for example, and we'll just put it on the bottom of this page, okay, is magnesium oxide is a metal oxide. Or we could have calcium oxide. All right, so as long as there's a metal bonded to the oxygen, it's a metal oxide. And I think that puts it, okay.
Thank you.
Now, I have the most amazing animation to show you. Okay, and we'll have to actually put I think we'll have to make a plan to put the link onto the website.
Okay, cool.
Okay, because I don't actually have it in the notes.
Okay.
But this is just the coolest animation. So what we're going to do now is we're going to look at a titration from a molecular point of view. Now, we didn't do a physical titration, but this is such a nice setup. The difference here is that the base, however, is in the burette. The acid is in the conical flask. It doesn't make a difference. We know the solution. We know the concentration of the sodium hydroxide solution. You have to know the concentration of one of them when you start. The nice thing is it uses a pH meter. Great way to do these. You would either do this with an indicator which changes color, which is much better, but that's okay. Now what we're going to do is, and I specifically want you to look at the bottom right-hand side of the screen, which shows you how the molecules change, okay? So we're going to begin the titration, and I'm going to add 5 moles of sodium hydroxide. And if you look carefully at the right, you saw a little bit of water being formed. The brown molecules are the Na plus ions. We're going to add another 5. Okay. And once again, we're now getting Na plus ions. The pH, if you look on your screen, is now 1,24. The pH is increasing. I'm adding a base. And in fact, we're drawing a really nice graph. Okay? So I just want to quickly, I want to make sure we're all in the right place. So we're seeing H2O molecules being formed. There's our Na plus. There's our Cl minuses, which we expected. And we're going to, and now I've got to get rid of this somehow. Okay, I want to get rid of the smart thing. Carry on. Okay. And there's still a smart thing, but that's okay. We're carrying it on. We're getting, sorry, the board's changed. The program's got better. I like it. Okay, so don't worry about the plaque that's carried on. We're going to add some more. Okay, and I really like the animation because it shows the little droplets in it. And as we watch, very slowly, now of course, we haven't actually added that much NaOH yet. Well, we have. We've added 20 milliliters. 20 centimeters cubed. That's a lot. And we still haven't seen too much of a change. I want you to see what happens now. Get to 25, and there's quite a big increase. We do it again, and look at what happens. Okay? And if we look over here, between 30 and 25, there's a sharp increase. Because what has actually happened, if we take the time to count, in my molecular structure, we've come to a place where the acid and the base are chemically equal. Okay? We've reached a neutral point. Now, this is a strong acid and a strong base, so that means it should be pH 7. Okay? Doesn't always happen. This is, of course, a simulation, so things could change. But now watch what happens when I add 5 more moles of NaOH. Now we change it to a base. Okay? We've gone beyond the point where it was neutral. Okay? We've gone too far, which is why acid-base titrations are so very exact. Okay? And it's a real skill, especially when you're doing it physically and you're having to turn the tap on the burette. I know I struggle with it, because you've got to make sure the tap doesn't fall off and all sorts of things. But literally, it takes 1 drop, and your pH changes. Now, I went from 7 to 12,02. That is a huge change. Okay? Huge, huge change in pH. If I add 5 more moles, only a small change. So now we're doing okay, now it's just doing its own little thing. Don't worry about everything else that's coming up. But what's happening here is that small part is almost the opposite of what we had at the beginning. And if we kept adding in base, we would keep it at quite a high pH. Okay, so we're not going to worry about the calculation because that's not what you do. But we need to talk about what indicators you would use. Okay, once again, learn, work. Okay, first of all, methyl orange, which is orange in an acid, yellow in a base. Methyl red, red in an acid, yellow in a base. Litmus, red and blue. Litmus can come in paper or liquid form, which is nice. Bromothiamyl blue, which is yellow and blue. And phenolphthalein, which you saw tonight, which is colorless and pink. It's a beautiful, I don't really like pink, but that was a beautiful pink. Hey, Looney? Because it was so bright.
Pink, but that color was
yeah,
really nice.
I'm allergic to pink.
Yeah.
I tell my children. Anyway, so it's a good thing my shirt didn't have to be pink. Moving on. Guys, please learn these. When it comes to things like universal indicator is literally a combination of indicators together, which is why it gives such a wide range of colors. You are not expected to know those. Okay, please do not think you have to learn them. You are expected to know these though. Okay, so make sure you know these ones. These are the common ones. You can also make household common everyday indicators. Black tea is an indicator. And how do I know that? Well, don't worry about what happens when you put milk in it because the white doesn't help from the milk. But if you put lemon juice into black tea, it goes lighter in color. Red cabbage. I did this once, never going to do it again. I don't like cabbage. And I boiled red cabbage at home. And cabbage has a very very unique smell.
Ah.
And so I boiled the red cabbage because I was all excited. I was a young teacher back then. And I made this beautiful red liquid, took it to school, and I was like, never again. It works.
Stinks.
Oh no, and it smells. My house smelled terrible. It was horrible. I'm sorry, it's just one of those vegetables. I just don't eat cabbage. Anyway, and then things like there's also flowers, different flowers change color. Okay, there's also, and I can't ever remember its name, but there is a flower that changes color according to the acidity of soil that it's in. So you actually can tell if your soil's too acidic by the color of your flowers. It's actually very cute. I suppose you could have a nice, pretty garden that way, I suppose. But yeah, moving on. Okay, that brings us to completing some equations. Looney, before I do this,
Yes.
and I'm squeaking again, are there any specific questions that have come up or not?
Let me just check quickly.
Because these are just equations. I just want to know if there's anything else that I need to re-explain, or whether I should just
do that.
do those, and then Looney's going to check.
Yeah.
I'm sorry, guys. My platform got fixed, and I think I moved
Do
it.
they even know you stand on one?
Yeah, no, sorry, I stand on a platform because I'm too short. Okay, it's not my heavy. I'm not that heavy. I don't make it noise when I walk. Okay, so complete and balance the following reactions in each case. Name the salt. Okay, very important. So we look at this and we go, now they're not always going to come in the nice way that I said acid plus. Because look here, this is a metal. Oh, maybe I should be able to write for something. Metal plus an acid. Metal plus an acid, look, and we go back and we go, gives me a salt plus hydrogen. So I have to have H2, and the salt's going to be the copper plus the chlorine. So it's going to be Cl2, put a 2 in there, and that's copper chloride. Okay? Next one. Ooh, Gabby, difficult one, second up. Silver carbonate plus nitric acid. Okay, silver carbonate plus nitric acid. It's a carbonate, so I'm going to get carbon dioxide and water. So CO2 plus H2O. Now I've got to work out the salt. Silver and the nitrate's going to go together. The hydrogen goes with the CO3. Here you've got to recognize the valency. The silver has a valency of 1, even though it's one of your transition metals, okay, which normally have a valency of 2. Silver has a valency of 1. It's the exception. Nitrate has a valency of 1, so this is quite nice. This becomes Ag, ooh, no, there we go, Ag NO3. Balancing this one could be fun. We actually need to put a 2 in front of that one and a 2 in front of the HNO3, and I think that's balanced. Let's just check. 2 silver, 1 carbon, 3, 6 oxygen. Oh, hang on, no, 9 oxygen, I can't count. 6 oxygen, 8 oxygen, 9 oxygen, 2 hydrogen, we're happy.
We've got a question.
Yay, let's do this, because we've got lots of those, yes.
Okay, Jancy Buanganga is asking, hey Tracy, water has a pH of 7. Does that mean that any substance that has a pH 7 is drinkable, like water?
It's neutral, but it might still be, water's neutral, okay? Be careful with mixing safe to drink and neutral. I would still hesitate to drink some stuff, even if it was neutral, because the chemicals just might be toxic. Remember, not everything not everything's either an acid or a base. That's only one section of our types of chemicals. Okay, so I wouldn't say yes, but I would say if you, yeah, in fact, I'd never say yes. Not in the lab anyway, because just because you get a pH of 7 doesn't mean that the salt or the combination of chemicals you made at the end isn't going to hurt you.
Okay.
Anyway, because of the chemicals.
Two
Yeah.
more.
Yes.
Lesufi Floyd Hotatsu is asking, is there any acid which has a pH of 0?
Yes, there can be those extremely strong acids. You can get close to it with hydrochloric acid and close to it with sulfuric. I just can't think of any offhand. It's like your pH of 14 with your bases. Okay, that's sodium hydroxide. So you can get it, but those are those aren't the sort of acids you're going to have lying around the home. It's also not, you might find them in the school lab, but you're not going to be working with them often. No.
Okay. Another interesting question, Masbula Lotok is asking, what chemicals are inside a bullet? Bullet.
Bullet.
Push, push.
Oh wow, those are got nothing to do with acid bases.
Okay, cool.
That's gunpowder.
Okay. Yeah.
And I have to be honest, I have deliberately not learned what's in there.
No, yeah, it's fine.
Because I can say, because I get, you'd be surprised. And I bet you anything it's a boy.
Yeah.
Yeah, no, it's a boy. See, I'm good, hey?
Yeah.
Let's make explosions.
I've seen gunpowder because my dad has a gun.
Oh, wow.
So he kept, like, he was a policeman, so he kept gun. Like, it's freaky, so I'd never go there.
Yeah.
I never want to touch the gun. It's fine.
Yeah, no, I'm a bit of a
Yeah.
girl. But it's also a dangerous thing. So
Yeah.
I would never, I have to be honest, even especially on television, I would
Yes.
never tell you what's in gunpowder.
Yeah.
But it's one of those things that unfortunately you can find on the net. But I'm going to advise you not to go play with it, not to try and make your own. It can be very uncontrollable.
Dangerous.
I have to be honest, I was one of those wussy girls who never did, you know, I'm not even going to say what chemicals you use because somebody's going to go try it. You know, when you make bombs at home with pool stuff and other stuff. And I was not one of those girls.
No.
Okay?
It's
I
unsafe.
ran a mile.
Don't do it.
And
at
I've
home.
heard some horrific stories. So
Yes.
please, guys, I know it sounds like fun and you see those ridiculous
Exciting,
YouTube videos.
blasting, bombing. No,
Uh-uh.
it's not safe, guys.
It's not. It really isn't. And you can really do yourself a lot of damage. And it seems quite a silly thing to do damage on. We okay?
Thank you.
All right, let's do a couple more. Now we've got metal oxide, sodium oxide plus sulfuric acid. This one's going to be a nice one. Metal oxide plus an acid gives me a salt, H2O, and water. In this case, it's going to be sodium plus the sulfate. So it's going to be Na2SO4. And remember, we've got part of the question was name the salt, so that's sodium sulfate. Next one is zinc hydroxide. So we've got our metal. This is actually quite a nice one. So it's an acid plus a hydroxide. So we're going to get plus water. You can see I know exactly where to start. Now you may think about it. The metal goes to what's left from the hydrogen that disappears off the acid. So it's zinc plus sulfate, which means I'm going to have zinc sulfate. And I just need to check this one because I know this one's not bad. It's one zinc, one sulfur, one oxygen. 4 oxygens here, plus 2, that gives me 6. 4 plus 1, this is a problem. So this actually, not there, needs to be 2 H2O. Okay? A good indication of how many H2Os I'm going to need, look at the combination of hydrogen and oxides. I think I have time for one more. Okay, and then I'm going to have to say goodbye. Potassium hydroxide plus nitric acid, nice and easy. Going to give me water. Okay, the potassium's going to go to the nitrate. We're going to get potassium nitrate, KNO3. Okay, guys, we're done for today. Next week, okay, we're going to look at the calculations. I haven't forgotten about them. I'm pretty sure some of you have done them. We're going to look at calculations and do a little bit more intense stuff, okay? So I'm going to say goodbye, and I will see all of you next week.
All right. Mindsetters, thank you so much for tuning in and joining the Vertically Challenged Girls in Studio. We are awesome, and all the best for all your exams and everything else in life. Until next time, guys, it is a goodbye from us.
A weak acid though, so what that means is that when this dissolves in the water, we get it to ionize, but we don't get a lot of product. There's very little of this. So because there's so little H3O plus, it's not very dangerous. Doesn't mean that it can't do damage, okay? So what I'm saying to you is don't go and drink a whole bottle of vinegar. You are going to feel fairly sick after that if you can actually get it done. Okay, so you got to be careful because remember your stomach's got acid in it. You don't want to add to that, okay? But lucky for us, vinegar, if you spill it on your table at home, isn't going to eat through your table, okay? Which is a good thing. So acids ionize, very, very important. A base, before we get there, now I've got a list here. And this, of course, is in the notes you can download. Please, grade 11s, you have to just learn this. This isn't something where I can say to you, look at the structure, look at how many hydrogens there are, because it doesn't work like that, okay? And these are your common acids. So these are the acids you're most likely to find at school. These are the ones we're going to deal with calculations, with experiments, all of that sort of stuff, and they Now, what's really important here is we define a strong acid, an acid which ionizes almost completely. Now, I've deliberately gone and bolded and underlined ionize because you've got to remember that all your acids are covalently bonded molecules, grade 11s. So that means they're not naturally ionic. So they haven't given away electrons, they haven't taken electrons, they're sharing them. So what happens is when the acid dissolves in water, we have to force it to become ions, and that's really, really important. With a strong acid, it desperately wants to become ions. So when we look at a strong acid like hydrochloric acid, when it reacts with water, and what's very important here is that we say it is reacting with the water, it's part of the reaction, okay? We end up with H3O plus ions because what's happened is the chlorine, the hydrochloric acid, has given its hydrogen away. It's acted like an acid. Remember, acids are proton donors. We did that last week. The water acts like a base, takes the hydrogen, ends up with H3O plus and Cl minus. Now, this is a strong acid, so that means when I look at this, if I could look at this solution from in a microscope and I could actually see the little molecules everywhere, there would be lots of H3O plus and Cl minus. And remember, I said to you last week as well that it's this H3O plus that makes it so dangerous, okay? It's the H3O plus ion that corrodes, that eats away skin and metal and all those wonderful nasty things. Moving on. So, when we look at a weak acid, and it's hard to see it from the equation because of the way we write the equation at this level. When you get to grade 12, you're going to do a thing called chemical equilibrium, and you're going to do the whole thing with reversible reactions, which you've seen. And this is, we're going to rewrite these equations with the sign doing this. Little sign to the right, big sign to the right, little sign to the left. And that tells me that I have lots and lots of ions in there. With my weak acid, like acetic acid or ethanoic acid, vinegar, okay? Remember, it's only that little hydrogen at the end that's important. The one that's bonded to the carbon isn't important, okay? It doesn't make it acidic. That hydrogen comes along, donates itself to the water, okay? Off it goes. Once again, we get H3O plus ions, and now we get the CH3COOH minus, okay?
Thanks so much for tuning in. Remember to hit us up on Twitter @LearnExtra, on Facebook. Our page is facebook.com/LearnExtra. And remember to download all the notes, the schedules, the videos on LearnExtra.co.za, and anything else you'd like to know about Mindset Learn and Learn Extra Live. Just simply go onto our website, guys, and work your way onto our page and all of that stuff. So with all that said, I will tell you about the Stars in Education Awards throughout the whole show. But for now, let's take it back to Tracy with our awesome lesson.
Thank you. Anyway, so we're starting with acids and bases, guys, and what we're going to start off with is just go through what we're going to do today. We're going to look at the difference between strong and weak bases. This is really important with weak and strong acids as well, and hopefully get the misconception of concentration out the way. We're going to discuss some acid reactions, so what happens when we put an acid with a base or an acid with a metal, which you did do in grade 9, hopefully. Discuss neutralization reactions, got a little bit of an experiment going for you, and Looney's upset with me because I don't know if I'm going to need her help today.
Why exclude me? But it's
fine. I know, I'm sorry.
It's fine.
And then we're going to discuss indicators, okay? So, starting with, what is a strong and a weak acid?
What's up, Mindsetters, grade 11s, it is your time for physical sciences on this beautiful Tuesday. I am Looney, and joining me in studio is one of my favorite teachers. Tracy, how are you?
Finally,
I'm good, thanks.
You can come back.
Yes, like all the time, Tuesday. Hey.
Absolutely, yes. There we go. Yes.
So what are we doing for the Mindsetters today?
Today we're going to carry on with acids and bases. Remember, guys, last week we did the basics. We started at the real beginning. What are bases? What are acids? Today we're going to look at strong and weak acids and bases. We're going to look at some common ones. We're going to do a attempt at a titration, not a complete one. And then we're going to look at some reactions. So you're going to be able to have to put, when I give you things, can you get me the products at the end, basically.
That stuff. So today it's not chilled. It's all
Today's
full on lessons.
Today's a little heavier than last week.
All right. Mindsetters, you heard it. We're going full on with acids and bases part 2. This section used to haunt me in my dreams back in the day. So I hope you guys do enjoy it. Thank you so